Okay, good morning slash good afternoon, everyone. My name is Somashekar Viswanath. You can call me Som. I'm a PhD candidate in the Civil and Environmental Engineering Department here at the University of Illinois at Urbana-Champaign. My advisors are Professor Jim LaFave, who is the professor and an associate head here in the same department, and Professor Dan Kuchma, who was previously here at the University of Illinois, but now is a professor at in the Tufts University. For my presentation today, I'll be talking about accumulation of damage in concrete when it is subjected to uniaxial compressive fatigue loading, which in turn results in degradation of strength and stiffness. Um, this very brief outline of my presentation today. I'll start with a very quick introduction, which in turn leads to motivation for the research. Then I'll give a very brief overview of the experimental work that was undertaken here. And then I'll start showing some results, starting with the results of the monotonic tests that were done first. And then it was a multi-stage experimental investigation that was undertaken. I'll be showing results from two different test series. The first one was known as the basic fatigue test series. I'll give a brief description. I'll show what, when I say concrete a damage accumulation, I'll show some photos showing what damage represented, and then stiffness degradation that resulted from this concrete damage, which is the first part of my topic. Then I'll give a brief introduction about the next test series, which was known as the strength degradation test series. I'll give a description, and then I'll show uh, some results which describe or which portray what strength degradation means because of the damage in the concrete. I'll wrap it up with some summary and conclusions. So a very quick introduction first. Um, Concrete is being used more and more in fatigue critical structures. Some examples include offshore as well as onshore wind turbine towers and foundations. Uh, Something that has been used quite a lot are highway and railroad bridges as well. Since they're being used in these fatigue critical structures, there's a need to have an up-to-date or a more advanced fatigue life models for concrete. Uh, this is not a new topic. Research has been going on for quite a while, but most of the research has focused on capacity, fatigue capacity of concrete. And when I say capacity, I'm talking about the number of cycles to failure at some given peak stress level. And in spite of several years or several decades of research rather on this topic, even to this day, there's no consensus on the use of any one equation. There are various equations out there and different researchers use different equations. And additionally, the focus on behavioral aspects is fairly limited. And considering the inherently nonlinear behavior of concrete, this is quite important, which leads to our motivation. Uh, and when I say behavior, I'm talking about strain behavior, stiffness behavior, damage mechanisms, the failure that we typically see, etc. So this was the motivation for our research, to do some experiments and identify which of the models were able to predict the failure number of cycles most accurately, and then look at and further the understanding of the behavior of concrete under fatigue loading, and if possible, develop a concrete material model that can be used when it is subjected to fatigue loading. And in order to do this, as I said in my previous slide, we undertook a multi-stage experimental program. In today's presentation, I'll be using results from two of the stages, which will come next. But before I go any further, I would like to clarify that the focus of today's presentation would be about behavior, specifically strength and stiffness degradation that arise because of some accumulation of damage when concrete was subjected to fatigue loading. I will not be focusing on the capacity and which models work best. Um, Before we go any further, I would like to give a very brief overview of the experimental work that was undertaken. So in order to do these fatigue tests, concrete cylinder specimens were cast in our lab. This is 216 concrete cylinders that were cast. These are standard dimensions, 4 inches in 4 inches in diameter, 8 inches in height. And we used servo hydraulic testing machine, the capacity of which was 100 kips. And in this next photo, you can see a cylinder specimen being placed in the servohydraulic testing machine. What you see here in green is known as an extensometer. Essentially, it's two LVDTs placed on either side of the cylinder, and we were measuring the change in length of the specimen as it was subjected to fatigue loads, and the output was an average of the two LVDTs. So with this, we started doing the experiments. The first one that we did were several monotonic tests, and the reason was we needed to know what was the average failure strength of the cylinder specimens to do the fatigue test. For example, in the fatigue test, we would go from some peak compressive stress level to some valley compressive stress level, and there was some proportion of this failure strength. So we needed to know that. And additionally, we needed also the average or the representative stress strain curve for analysis of fatigue results. So for this, we conducted monotonic tests throughout the duration of the fatigue tests at regular intervals, roughly every 10 days or so. And some of the monotonic stress strain plots are shown in this figure here in the various colors. And we also needed, as I mentioned before, a representative stress strain curve. So we use some existing equations, and we tried to match the average failure strength, FCM, and the strain at this average failure strength with this representative curve. And we saw that it was a fairly good match. So in all our fatigue analysis, we used this representative curve, which is shown in the dashed black line. Because it was a good representation, an average representation of the various monotonic stress strain curves. So the next thing, having obtained uh, the monotonic results, we started with the next test series, which the first one was known as the basic fatigue test series. So I'll give a very brief description about this test series here. In general, in this test series, we tested concrete cylinders under fatigue loading in uniaxial compression. And by that, I mean there was a peak stress level and a valley stress level, both of which were compressive in nature. They were held constant, and fatigue loads were continuously applied at these levels at some specific frequency until failure. A typical loading waveform is shown in the figure on the right here. Uh, so the peak stress level is indicated at the top, the valley stress level here, and at some fixed frequency. In this figure, we are showing the use of frequency of 2 Hertz, which was fairly commonly used in our test series. Now, the other decision that we had to make was to select what was the peak stress level and what was the valley stress level that we wished to investigate. In order to do this, the goal was to focus on high cycle fatigue. And when I say high cycle fatigue, that roughly corresponds or translates to failure number of cycles somewhere between 1000 and 1 million fatigue loading cycles. So in order to do this, we looked at some existing predictive models, and the model that we looked at used the peak stress level called Smax and something known as a stress ratio R, which was the ratio of the valley stress level to the peak stress level. And we looked at what are the possible combinations that we could test so that we were in the high cycle fatigue domain, and we came up with a range of values so that there were different values for the peak stress level and different values for R as shown here. So for example, one of the combinations that we chose was the 80% and the 20%, which is the figure shown on top as well. So the peak stress level was 80% of the average cylinder compressive strength in monotonic loading. So on the y-axis, it's normalized with that. So we went up to 80%, and the valley stress level. So for the 80% and 20%, it was the valley stress level S min was 20% of 80%, essentially 16% of the average cylinder failure strength. And in this case, as I mentioned before, we went at 2 Hertz, which essentially meant 2 complete loading cycles in every second. And with regards to the data acquisition, obviously we were obtaining the number of cycles to failure, but as I mentioned before, that's not the focus of the presentation. We obtained the change in deformation or the change in displacement readings in each cycle, from which we were able to obtain strains, from which we were subsequently able to obtain stiffness information as well. So with this description, I'll start showing some results. But before I do that, I wanted to show what we meant by concrete damage. So during these fatigue tests, something that we observed were some surface cracks appearing on the concrete cylinders, and with increasing number of cycles, there was progressive increase in the length as well as width of these surface cracks. Which is what we are referring to in our research, and I am referring to in this presentation as damage. So in this first figure here, this is roughly at around 60% of the failure number of cycles. We see these small surface cracks appearing on the surface of the cylinders, and with increasing loading, the cracks they start connecting to one another, and then with further increase, they increase in length and in width. We can clearly see that they are much wider here, and there's some small spalling that is happening as well. And with further and further increase in the number of cycles, the damage level continuously increased, as you can see in these plots. So this final one is actually very close to failure. If you see closely here, you can clearly see that the crack is separating from the surface of the concrete cylinder. So if we use that as the starting point, it was, as I said, very close to failure, and with a few more cycles of loading, it resulted in complete cylinder failure, as seen in these next two plots. In order to show what a typical fatigue test would look like, I have a small video here, which is towards the very end. It's the same cylinder starting at about this phase. Okay. There appears to be a slight delay between the video, but you can see that with increasing number of cycles, the crack widths actually increase. So I've zoomed in a little bit now. The cycles are increasing, and a few more cycles of fatigue loading, and it leads to damage, as seen here. Um, so so when I said damage, it's the surface cracks that we were seeing. And since we saw such damage, we anticipated, or we hypothesized, that there should be some kind of degradation of strength and stiffness characteristics. So the first thing that we investigated was degradation of stiffness under fatigue loading. And when I say stiffness, we had the peak and valley stress levels, corresponding to which we had the peak and valley strain levels. So just using that, we obtained a secant stiffness value in each cycle. And then we compared the magnitude of secant stiffness at the start of the test versus the end of the test. This is for all that. What you see here in the right in the plot is the secant stiffness comparison at the start and end for all the tests that were done as part of the basic fatigue test series. Some observations, you can clearly see that the initial secant stiffness, there's some variation, but this level of variation is expected in concrete. They all hovered around sort of a mean value. On the other hand, when we look at the final secant stiffness, we can clearly see that there's a trend that the final secant stiffness value increases with increasing number of cycles to failure. And immaterial of what the number of cycles to failure were, we could clearly see that the initial secant stiffness was much higher than the final secant stiffness, which indicated that there was definitely degradation, which was our hypothesis. To investigate this further, here we are only comparing the initial and the final values. We started looking at the progression of secant stiffness through the fatigue loading process, which is the focus of the next slide here. In this slide, there are two kinds of plots that we are showing, and the two plots shown on the top are for one specific fatigue test combination, and the two plots shown on the bottom are for another fatigue test combination. And in the right, so we computed the secant stiffness at every cycle, and we just essentially plotted them and observed a progressive or continuous degradation of secant stiffness through the fatigue loading process. These are typically called as secant stiffness evolution plots. And we could see that there was continuous and progressive degradation of secant stiffness. Additionally, what we did was to visualize the secant stiffness. So we connected the peak and valley stresses and strains by straight lines to represent quote unquote secant stiffness lines. And with increasing number of cycles, we can see that the slope becomes smaller and smaller. So there was definitely softening of secant stiffness as we went through. What you see here was the average monotonic stress strain curve that I showed previously when I showed the monotonic stress strain results. So we could clearly see in both the plots that there was continuous degradation of secant stiffness with increasing number of cycles. In the next plot, I show this figure, but I also add the number of fatigue loading cycles, as you can see here. So in this, it's the same idea. We have the stress and the strain axis, but I've added a third axis showing the number of cycles. So as we go into the page, the number of fatigue loading cycles is increasing. And what we see here is the average monotonic stress strain curve, just for reference. And each of these lines, as I said previously, represented the secant stiffness at those many number of cycles completed. So we can clearly see that with increasing number of cycles, essentially as you go in, the slope of these lines becomes softer and softer. You can clearly see that they're becoming more and more towards the x-axis, which indicated or which verified our hypothesis that there was definitely degradation of stiffness when concrete specimens were subjected to fatigue loading because of accumulation of damage. So this verified our first hypothesis. In order to verify the second hypothesis, we undertook a second test series known as the strength degradation test series. Similar to the previous case, I'll give a brief description and then go over the results. This is the second part of my presentation for today. With regards to a description of the test series itself, once again, this was fatigue testing of concrete cylinders. The peak and valley compressive stress levels were held constant. The change here was that we did not load it until failure in fatigue loading. We only loaded it up to some proportion of the failure number of cycles. We stopped the test and then we unloaded it, and then we reloaded the fatigue damaged specimen in monotonic loading until failure, so that we could see and compare what is the strength of a fatigue damaged specimen versus what was the strength of an undamaged concrete cylinder specimen. The goal was obviously to evaluate or to check if there was any strength degradation, and as I said before, the number of cycles that were applied was less than the failure number of cycles, and we were collecting strain data throughout the test. Excuse me. So there was one challenge here. So when I said we were stopping the test before failure, we had to know what was the proportion of fatigue loading that was completed. For example, if we take one combination, say the 75% and the 10%, in when we did the basic fatigue test series, we did various cylinder specimens. The failure number of cycles varied from 10,000 to roughly 60,000 cycles. So if I wanted to stop a test at 50%, should I take 50% of 10,000 or 50% of 60,000 was the question. And because of the inherent variability in concrete, compounded with the inherent variability in fatigue, this is fairly common and expected, but for it presented quite a big challenge for this test series. So in order to do that, we had to estimate the failure number of cycles real time. And what we did is shown in the next two slides. So in the strength degradation series, so for the 75% and 10% combination, which was conducted at 2 Hertz, we conducted several tests. And what we did was to observe the variation of the peak displacement with time. So on the x-axis, you have time here going in minutes, going from 0 to 60 minutes, essentially for 1 hour. It was the same combination, 75% and 10%, and various tests were done. And in the various tests, we can clearly see that the variations are quite different. So we had to estimate what could be or what would be the failure number of cycles having known this information. And to do that, we used two things. One was the slope of this line, So what we show here are the peak displacements. From peak displacements, we went to peak strains, and from peak strains, we looked at the slope of the lines. Those are known as the strain gradients, as well as the magnitude of the peak strains at the end of the fatigue loading phase. And based on that, we would estimate what would be the failure number of cycles. Therefore, what proportion of failure number of cycles have we completed? And in order to do that estimation, we use the data from the basic fatigue test series. So in the basic fatigue test series, we again looked at the strain gradients in essentially the slope of the strain in sort of in this middle phase in all the tests. So we looked at the strain gradients and we plotted the strain gradients versus the failure number of cycles, and we obtained a linear relationship. We observed a linear relationship. Since we obtained and we obtained it with a very high confidence level. Since we obtained that, we observed the tests in the strength degradation series, computed the strain gradients, and using such an expression, we were able to estimate what would be the failure number of cycles. And we used it in conjunction with the values of peak strains as well to make any minor modifications that we had to. And having known that, we could then estimate what proportion of fatigue loading was completed. With this, let's look at some results. So we were computing, or we were obtaining strains throughout the test. So this is a typical strain evolution in the strength degradation test series. So in each test, we obtain the strains at some data at some specific or predetermined rate of data acquisition, which is shown in these solid black lines as hysteresis loops. I have been talking about secant stiffness lines. Those are shown in this plot as well by these dashed blue lines, essentially connecting the peak and valley stresses and strains. And as I said before, after, we did not do fatigue loading until failure, but rather after some point we stopped the fatigue loading, and then we did monotonic loading, and that included an unloading phase, essentially removing all the load, and then we held it constant at a very low value of load, which was known as the dwell phase, and then we reloaded but in monotonic loading until failure. And we observed what was the failure load, compared it with the failure load of an undamaged cylinder, and then compared to see if there was any strength degradation. This was the general idea. So now some specific results from the strength degradation test series. Once again, I'm looking at the 75% and 10% combination. So for this one, in magenta, you see the monotonic stress strain curve of an undamaged specimen, and what you see here is the fatigue is a monotonic curve of the fatigue damaged specimen. So first, it was the 75% 10% combination, and once we stopped it, we estimated what would have been the failure number of cycles. So correspondingly, we estimated that to be about 25% complete. And then once we did that, we did the monotonic test. So there was the unloading specimen as shown in green, then a dwell portion which is shown in orange, and then we did a monotonic test uh, which is known as the reloading, and we did it until failure, and we compared this failure value with the failure value of the undamaged specimen. In this case, essentially at 25% complete, the failure load was very close to that of an undamaged specimen. We did that similarly with another test, the same 75% and 10%, but in this case we estimated that we had completed about 97% of fatigue loading, and then again there was unloading, 12, and then reloading. And then in this case, when we compare the failure load with the failure load of an undamaged specimen, we can clearly see that there is strength degradation. So we did this for a wide range of fatigue load completion percentages. So it was, again, all the tests shown here are for 75% and 10%, and the failure number of cycles range from 15% to 97%. So in the two slides before, I showed something that was for 25%, that is this plot shown here in yellow. And then in the previous slide, I showed the 97% completion, which was this plot shown here in cyan or light blue color. What we can clearly see is, with increasing number of fatigue loading percentages, the strength of the concrete of the fatigue damaged specimen decreases in comparison with the strength of an undamaged specimen. So for an undamaged specimen, it was close to 85 kips, when it was 97% complete, the monotonic strength was only 74 kips, which roughly showed about a 20% reduction. So with these plots, we were able to confirm that there was definitely strength degradation associated with damage incurred in the specimen under fatigue loading as well. We did this with various combinations, and then when we observed, we see that up to about 60 or 65% completion, fatigue loading completion, there is no strength degradation, and with further increase, there is continuous and progressive degradation of strength. Quite interestingly, it's at around this stage that we started seeing surface cracks appear on the cylinder specimens as well. Once again, this confirmed our hypothesis that the damage that occurs in the cylinders results in strength degradation in concrete as well. So since so those both the results sort of confirmed our hypothesis, which leads to my summary and conclusions. From this study, we did multiple fatigue test series. We gained better understanding of concrete behavior through the fatigue loading with regard to strains, stiffness, damage mechanisms, failure mechanisms, etc. And as a first step, we observed that there's definitely damage, which causes, as a first step, stiffness degradation that was verified through the basic fatigue test series, and strength degradation that was verified through the strength degradation test series. And the amount of strength degradation was related to how much of the fatigue loading proportion was complete, and the results from both the test series essentially verify our hypothesis that the damage uh, that is caused through the fatigue loading process results in degradation of both strength and stiffness of concrete. With that, I would like to conclude, but just before that, a quick acknowledgement to the fellowship that was provided by my department, which helped me through this process. The CE department machine shop people who helped me in the testing, and definitely my advisors for guidance and as well as for support. I would like to thank you all. If you have any questions, I'll be happy to answer them. And for your reference, I've also included my email ID here in case anyone has any questions and would like to contact me. This is once again the video of the specimen that failed. I'll just play it here at a low volume in case anyone is interested to see the failure mode. Okay, thank you everyone, and I'll be happy to answer any questions.
Great, thank you, Som. We do have a couple questions and we have a little bit of time. I think you described this in some of your later slides, but would you mind defining fatigue damage, what you mean by that?
It's by fatigue damage. When we did the fatigue test, what we observed was, I want to see if this works. Let's see. No. Okay. Yeah, here we go. So okay, so when we did the fatigue test, initially we started seeing the surface cracks develop at roughly about 60 or 70% of the failure number of cycles. And with increasing cycles, we started seeing the cracks become bigger and bigger. So there was definite damage in the specimen. So we were just referring to this as fatigue damage. And because we saw such big cracks, we hypothesized that, okay, then there must be some other effects on the behavioral aspects, specifically strength and stiffness, and which is what we investigated in this investigation.
I think that leads me to another question that has come up. Well, that's interesting, the observation of damage that you're looking at in these fatigue tests. What is your motivation for the work, or what types of applications do you think can benefit from what you've done?
That's a very good question. So one of the most important things is now concrete is being used, or as at least being considered as an alternate option for wind turbine towers, onshore and offshore, and definitely for the foundations. In a typical concrete bridge, we might expect to see about 20 million cycles of fatigue loading, in a concrete wind turbine tower, which has a fatigue life of about, which has a design life of about 20 years, the anticipated number of fatigue loading cycles is 500 million. So there is no data that is there that checks the capacity up to that level. So we had to investigate, and we had to know better what was the capacity of concrete when the number of cycles could be as high as 500 million, which is why we started this investigation.
Thank you for the clarification. We had a question early on about how you prepared the ends of your samples. Did you grind them or?
Again, that's a very good question. So in some, not us, in a few other research that has been documented, they cast much longer specimens, 4 inches by what we cast were 4 inches by 8 inches. In some cases, they do 4 inches by 12 inches, and then they grind the specimens. What we did, which can be seen partially here, was to use sulfur caps in order to ensure that the ends were smooth. So we would take the cylinder specimens, there was a mold, and then place sulfur caps at both the top and bottom of the specimen to ensure that there was a smooth and uniform contact surface between the loading platens and the cylinder itself. And for people who might not be aware, the sulfur caps are sort of these darker colored, I would say dark brown, that you see in these photos here at the top and bottom of the cylinder.
Did you do any additional comparison with non-sulfur capped cylinders to compare how that might influence your results?
No, in our test, we did not do that. We had the option of using rubber pads that we could have used, which is essentially steel caps with rubber pads that can be placed on the cylinders. Again, I've seen many investigators use that, but we just decided to go with this option because this is something that my advisors have used in the past and they were comfortable with it. So they recommended that we should just stick with that, at least for now.
Regarding the fatigue range, the load range that you selected, how did you decide on that load range?
Okay, I'll do. Yeah. So here, so our goal was to select the peak stress levels and the stress ratios such that the anticipated failure number of cycles would lie between 1000 to 1 million. Anything less than 1000 is typically considered low cycle fatigue, and those kinds of fatigue applications are important for high load events, essentially something like an earthquake. In a wind turbine tower, we don't anticipate that the stress levels are going to go beyond, say, 80% or 85%. And to do 1 million cycles of testing in our testing machine, which had a capacity of 100 kips, that would take us about 5 days of continuous testing. So we kept an upper limit of 1 million. So that set the range. So now having known what the range was, we used some existing fatigue life predictive models, and then we selected the peak and valley stress levels so that the failure number of cycles was less than 1 million but greater than 1000. And we wanted to have a good range of peak stress levels and a good range of valley stress levels. So we chose a wide range in both of them and tried to cover as much base as possible.